Hi everyone, this is Ahmed. I'm a PhD student at IHE and TU Delft. Today I'm going to speak about reduced complexity modeling of shoreline response behind offshore breakwaters. But first, let me introduce my supervision team and the co-author. First, Professor Dan Roelvink. He's the founder of Shoreline S Model. Then Baz Huisman and Johan Rein, co-mentors and the co-founders of Shoreline S Model, and also Dr. Susanna Costas and Dr. Yab Ninehouse, which is my co-supervisor also. I'm also working at SEMA and University of Algarve in LACE project, which is funding of this research. So let's go. As you know, since 1960s, in many places around the world, they start to use the detached breakwater or the offshore breakwaters. As you know, because it reduces the wave behind, and also it helped to build a land behind that you gain more land in terms of salant or tombolo. So it's the challenge for the engineers is how to predict the shoreline response behind these structures. And in order to solve that, there are several ways. For example, they can be done using the shoreline analysis empirical formulas, or it could be done, the first one maybe not the accurate one. The second one could be done using the 2D or the 3D models, which is more accurate but it's highly computational cost. The third one could be the physical models, but as you know, it could be very costly in terms of the money. And the fourth solution could be the one-line models, and you know that is cheaper in terms of the money and cheaper in terms of the computational cost. That is why we prefer this solution to go. I'm going to go through some history or literature review of the shoreline modeling, which will help me to introduce to my topic. So when we talk about the shoreline modeling, first of all we should start from the Bernard Consider, which is the first one who introduced the mathematical model for the one-line models. In 1984, the Shoreline Protection Manual, they provide us with known SERC equation, longshore sediment transport. Also in 1991, Campus provide us with another formulation for the longshore sediment transport. In 2000, Campus and Davis, they provide us with some formulation to calculate the diffraction coefficient behind the breakwaters. And in 2000, Davis in his PhD thesis, he introduced a new method to calculate the diffracted wave behind the offshore breakwaters. And in 2007, Hanson al. introduced the tidal current, or they added the tidal current or the wind-induced current to the longshore sediment transport. And Harris in 2015 introduced us two formulations to calculate the diffraction coefficient behind in the shadowed zone and in the transition zone, which is still affected by the diffraction. Before 2017, there is a lot of one-line models that are commonly used, like Genesis, like Laidback, like Online, GenCAD. So many one-line models that was performing good. However, they have some limitation because of the grid system, that if you have, for example, island, or if you have this high curvature shapes, that could make it was not easy to simulate the shoreline. In 2017, Professor Dan Roelvink introduced the Shoreline S model. The main idea was the existing one-line models. If this is your shoreline, so you divide it into some segment, but in order to define to the model, you have to use a grid. But that puts some limitation in case if you have, for example, the highly curvature coastal shapes. So Professor Dan Roelvink decided to get rid of the grid, and he used a free grid system. So he defined the shoreline by its global coordinates, like x and y points. And then in order to calculate how the segment of the shoreline move, so for each segment you calculate the transport rates, and then for each two you, based on the two different transport rate, you can calculate the point in between, how much it should go. And using this free transport, that allow us to simulate different process. For example, the barrier over was able to be simulated. For example, this Alaska, one example from Alaska Barrier Island. As we can see here, the barrier rollover is managed to be simulated in the model. Also the inlet migration, and this is a case study in Senegal, where Professor Dano was able to simulate. This is the observed one, and this is the model, was able to do the inlet migration process. And also the spit growing, and this is easily spit from Erie Lake, which also demonstrated that the model can be able to handle this process. So now, as you can see, the models are able to simulate such process. Now we want to make sure that the model also is able to handle the wave diffraction process. So in order to do so in the model, the model is based on the longshore transport formula. So here there are three main challenges. First, the wave height and the wave angle, and also the breaker line, because here we use breaking wave condition. So we need to determine where is the breaker line. So for the wave height, as we produced in the literature at the beginning, we use the Kempf's method to calculate the diffraction coefficient, and this showed if we calculate the coefficient from one tip, and that when we combine from two tips. And for the wave angles, we have tried three different approach. For the sake of time, I will refer to the reference that you can read them in details. But for briefly, we can say the first one, that Davis approach that we has mentioned in the literature at the beginning. So that he assumed one point that refract the wave, and then he provided the equation to calculate the wave direction behind. The second one, we add a little modification to Hurst approach, so we calculate the delta from the transition line instead of the shadowed zone, then we multiply by 1.5 theta. And finally, we introduced a new method that we call the Roelvink approach. The idea behind this is that we gradually change the wave angle from the transition line to the point behind the breakwater. So we calculate the angle delta and between the two lines, and then we add it to the angle alpha, so we have the new angle. So we make sure that is gradually changing from the transition line to behind the offshore breakwater. And this is how the three different method looks like, and that is if we plot them together, as we can see that how the abyss looks, and then Roelvink, and then modified is more toward the behind the breakwater. The third challenge is the breaker line, where to put our breaker line. So if this is our shoreline and if this is our breakwater, in the current model they usually use a parallel breaker line. If we think about how the breaker line should look like, so behind the breakwater we know that the wave height is reduced, so that means the breaker depth should be also reduced, so the breaker line should be look like something like this. So then we make use of the free grid system of the ShorelineS. So if this is our segment of the shoreline, for each segment we have a breaker point, and we calculate this breaker point based on the DIM profile. So we know the breaker depths and use DIM profile to calculate this breaking point. So the breaker line would be something like look like this, and during the simulation will be moving like this. In order to validate our methodology, we can do three things. We can compare to the lab test, we can compare to empirical formulas, we can compare to real case studies. In this presentation, I'm going to show comparison to the test that we have done against the empirical formulas. So we set our criteria that for the tombolo, based on Kong 2016 and so on Dremel 1987, that when the breakwater length is more than the distance to the shoreline, then we expect a response to be tombolo. and if it less than that, that means we expect salant. And so for the salant, we are going to test against two empirical formulation for the salant. So we design our test that we are going to test the three approach, and for each approach we are going to see if we can rely on the diffraction, Shoreline refraction coefficient, or two of them or one of them, which is diffraction. So for each one we run 12 tests that we make sure that we expect among this result tombolo, salant, and limited response, and it is the initial parameter for this test. Also, we used this transport formula that taking into account wave height gradient. So here is the result. When we plot the result of the Davis approach, as you can see, it was following the curve of salant. However, when in this area the breakwater length is more than the distance to the shoreline where we expect tombolo, it doesn't happen. In the modified Harvest, it managed to give tombolo at when it should give. Same for Roelvink approach. However, we prefer the Roelvink approach in terms of how the way it built. For example, if we look here, we have two examples of how the tombolo. Here, as you see here, Harvest approach doesn't, the behavior doesn't look normal. And also we tried to run a multiple system of breakwaters, and that's how it looks like after 8 years and after 24 years, and as you can see, it managed to fill the area behind. Also, we run a case study in Egypt, which is Elghandour from 1990 to 2010. So initially we expect in 2002 that this area start to fill a little bit, and then totally fill in 2011. I'll give it a little bit push. So in 2010 it managed to fill this area, and also it filled it totally in 2010. However, the behavior, there was more stability needed, and still a lot of improvement still needed. So our conclusion is that validation test we have done showed the capability of the model to simulate the shoreline response behind the breakwaters. The free grid system gave us two advantages, that we are able to track the breaker line and also to form a tombolo. However, we still need more verification test and refinement to the proposed approach. Now we have ongoing research. We have research on the wave diffraction to improve the function and all this approach, and try a new approach, which is I'm doing in PhD. Also with in a cooperation with a master student, Tim from TU Delft. He's working on the wave diffraction behind the shoreline structure. Also Ahmed is going to start soon, from Egypt. Is going also try to validate the model with different case study. And generally for the ShorelineS, we are working on the rollover, the barrier rollover, and the tidal inlet migration. And also with a master student, we are working to and using the data assimilation with ShorelineS. If you need more information, the first one, that is the published paper about the model, and the second one is a master thesis, which will has more information about what we presented today. Thank you, and hope you enjoyed this presentation.